So without further ado, it's a great pleasure to introduce Marina Iliopoulou from the University of Kent, and she's going to be talking about discrete Kakeya-type inequalities.
Okay, thank you very much everyone for inviting me. So my motivation for these problems, the point line incidence problems, comes from harmonic analysis. In particular, there we have problems that have to do with waves that evolve inside tubes in space-time. And we would like to understand how these waves interfere with each other. And these are very hard problems. So since they have a point tube incidence flavor with oscillation, we try to create more toy problems that have a point line incidence flavor and try to understand, get some inspiration from what happens there to understand the harder problems in harmonic analysis. And it seems that indeed algebraic techniques that have recently revolutionized incidence geometry are starting to yield results in harmonic analysis as well. Okay, so please feel free to stop me to ask questions anytime. So yeah, my motivation comes from Fourier restriction theory. So this conjecture says, let's take a curved surface inside Rn. And let's take a function that's defined on that surface. Can we understand its Fourier transform? What does its Fourier transform look like? So the Fourier transform of such a function will be defined in a standard way. At every x, it will be the integral of the function, but this time defined, of course, on the curved surface with respect to the Lebesgue measure induced by the measure in Rn. And we integrate against a twist that has to do with the point x, where we evaluate the Fourier transform. So what happens is that if we just look at a little cap on this surface, and we look at our function only on that cap, then if we take the Fourier transform of that, it will evolve as waves inside parallel tubes, fat parallel tubes disjoint to each other. And the direction of these tubes will be the normal to the cap. That is the case. And now if I take another cap somewhere on the surface that has some normal to the surface, and it will give rise to another family of parallel tubes parallel to that normal, and the waves coming from that cap only will evolve inside those tubes. So as the tubes intersect each other, the waves interact with each other. And the question is, how do they interact? So you see that if the surface was flat, then all the caps along it would give rise to the same family of parallel tubes. So because they would all have the same normal. So we'd expect that the waves would pile up on top of each other a lot, and there would be a lot of constructive interference. So the waves would become very big. Well, now as we start to arc the surface, the tubes start to intersect less, and hopefully the waves that interfere are out of sync with each other, and we hope we'll have a lot of destructive interference. So the curvature of the surface we expect will give us a lot of destructive interference. So that is what the conjecture says, that in principle we have so much destructive interference if the original surface has non-vanishing Gaussian curvature, that the p-norm in Rn of the Fourier transform will be smaller than the p-norm of the original function, which is defined on a lower dimensional set, and for a wide range of exponents. This is only known in R2, and it is open, it's a conjecture by Stein, and it is open since the 70s. I should say that this is not a random, I mean, this problem has a lot of applications in geometric measure theory, in PD. So for instance, if we have the paraboloid as our curved surface, then the Fourier transform of a function is essentially the solution, the general solution to the Schrödinger equation with some specific initial data. If we look at the cone instead, then we get the solution to the wave equation. If we look at the sphere, this is associated to the Helmholtz equation. So there are a lot of connections there. Okay, since this problem is very hard, a first step to understand it would be to completely remove the oscillation. So the oscillation is difficult of the waves. We remove it, so we just look at tubes that point in different directions. And we want to understand how they overlap. We'd like to know that they don't meet very often. So whatever constructive interference might happen doesn't happen often. So removing oscillation, we actually get the maximal Kakeya conjecture. It's not easy, really. This is still an open problem. But in any case, we have a bunch of tubes that are all congruent. So they have the same cross-section delta and the same length, 1. And they point in different directions, meaning that the angular, so between any two of them, we have angle at least the cross-section delta. And we'd like to show that tubes like this that point in different directions don't meet very often. So on average, we'd like to know that through every point, we have very few tubes passing. The tubes should essentially act as if they are disjoint. Okay, so the conjecture, if we think of it this way, we'll say the following. It says, let's take any point x where tubes may meet. And what we do is we look at the number of tubes through x. So we look at all the tubes that pass through x. Okay. We want to show that this number is, in some sense, a constant in principle. So what we do is we raise it to a large power, we'll say what, and we expect that this number to a large power will behave sort of similarly to the same number to the power 1. So if this is true, then in some sense, the tubes behave as if they are disjoint. Only very few pass through each point. This won't be true for every x, but the expectation is that it will be true on average. So we integrate over all x in Rn, and we expect that such a thing should be true. By the two wiggles, I mean that there may be, so the left-hand side may be bigger than the right-hand side by a logarithm of 1 over delta or something. So there is a logarithmic loss potentially. They are not just comparable in terms of order of magnitude, but anyway. And the conjecture says that the largest power for which we expect this to be true in Rn is n over n minus 1. This is the conjecture. And we see that the right-hand side is a very easy thing to understand, actually. We can pull out the sum, and it becomes the sum of the sizes of the tubes. And we know what size each tube has. It's the cross-section to the n minus 1 times 1. So this is the size of each tube times the number of the tubes. Okay, so this is what the conjecture says. And this is very difficult to prove. So to understand this a little better, we can try to shrink the tubes down to lines and see if we can get a similar estimate for lines. Can we show that under conditions, lines don't overlap, don't meet very often? Okay, so the idea here is that the tube is like a line, a fat line, and every delta cube, little delta cube along it is just a point. That's what we pretend to have. So we just try to change the inequality a bit so that it looks like more about lines and points. Okay, so the left-hand side, we take every little delta cube and we count the number of tubes through it, and we raise it to the appropriate power, and we just multiply with the size of each delta cube at the front. So this is the exact inequality, and I put the deltas all on the right, and this is what I get. For every little cube, I look at the number of tubes through it, and I raise it to the power, and I hope this is small. Okay, when I shrink down to lines, I don't want to impose any angular separation between the lines, because the angular separation has a lot to do with the fact that the tubes are fat. They have a width delta. The lines will have width 0, so I don't want to impose any condition on the separation of the lines. So I'm trying to find the right-hand side that doesn't depend on delta anymore. And we notice that actually the right-hand side is always at least the number of tubes to a specific power. If I rearrange this, it becomes a very trivial inequality. It says that the tubes can't be too many. They can be at most as many as the directions they can have, which are the delta caps along a sphere. So if I look at all the possible directions that are delta separated on a sphere, they're delta to the minus n minus 1, so that's how many tubes I can have. So we do have that the right-hand side is always bigger than this quantity, and we'll try to see if we can expect a similar estimate for lines. So that is what we get. We can ask if we just have a bunch of lines without any assumptions in Rn, and we look, okay, not at all the points in Rn exactly, but at the twofold intersections, at the points where at least two of our lines meet, just like in the picture. Now, if I look at all the lines through each point and they raise to the same power, do I have this kind of control? It's a little better in numerology than the Kakeya conjecture. And the wiggles mean that I may have a log of L on the right-hand side. Okay, so one can of course see that this won't be true without any conditions. So this would say that all twofold intersections are very, very few. At most, the number of lines to a part that looks more and more like one. And we can see that this fails if the lines lie all on a plane. So if all the lines lie on a plane, then everyone can intersect all the others. And we have L choose two twofold intersections. So the left-hand side is bigger than L squared. So we definitely need to impose some conditions on the lines. And the problem is that this clustering on a plane means that the problem is not really n-dimensional. It's more like two-dimensional. So what we'll do is we'll try to impose some higher dimensionality at each point. So we'll look at points where the lines that meet there actually span Rn. Their direction span Rn. And these lines we call, these points we call joints. And you see easily that if I just start raising one of these lines out of the plane, I will lose all its intersections with the other lines. So we'll get definitely fewer incidences. So that's the points I focus on. So a point in Rn that is a joint formed by a family of lines if the lines through the point span Rn. So in R2, it's very easy, it's very simple. Any two intersecting lines form a joint there at their intersection. But in higher dimensions, coplanar lines in R3 say don't form a joint where they meet. We need at least, we need non-coplanar lines to form a joint. Okay, so we'll ask the same question about incidences, but we'll only add overall joints formed by this family of lines. So that is a conjecture. And actually I've removed the logarithmic loss. I don't think it should be there. So in the Kakeya conjecture, the logarithmic loss depends, it has to do with the volume of the tubes. And I don't think it should be here for lines, which have no volume. Anyway, so if we look at all joints and we count the number of lines through each, and we raise to this power, can we control this quantity? What we do with Tony Carbery is that we show that this holds in R3, and we give some information on quasi-extremals, meaning that when the left-hand side is almost equal to the right-hand side, or comparable, what the joints and lines start to look like. Some structural information about the joints and lines in quasi-extremal configurations. Before I explain more, I'd like to give some little history about who has worked on this. So on the left column, I have the people who counted joints without multiplicities. So here we do have a multiplicity for every joint that's higher the more lines pass through it. But the question to begin with is, can we just say that the joints is smaller, the number of joints is smaller than the right-hand side? And this was first proved in R3 by Guth and Katz, and later by Kilodraun, Kaplan, Sherrier, and Suste in higher dimensions. And all techniques were algebraic. So there is some algebraic structure behind this, some algebraic nature underlying this problem. And on the right side, we have people who worked on counting joints with multiplicities. So there are these three works, and I should say, so the motivation and the estimates are about an estimate that can hold in all fields, not just Euclidean space. But the thing is that this conjecture I have up here can dramatically fail in finite fields. It cannot be true. It's very easy to find counterexamples. And it's not because of the log loss that I removed. It just doesn't hold. So there is a slightly weaker estimate, though, that holds in all finite fields. This was proved by Zhang to its full generality. And it has to do with the number of linearly independent lines through each joint, rather than just the number of lines through each joint. Anyway, here we're just focusing on a better inequality that has no chance of holding outside Euclidean space. Well, in finite fields anyway. So, right. This is the theorem, the inequality in R3. So the exponents become 3/2. And about the structure that we have for quasi-extremals, let's think first. There is a very easy situation where the left-hand side is equal to the right-hand side, where all the lines pass through the same joint. So we have just one joint, and all the lines, L of them, pass through that. Then the left-hand side is L to the 3/2, but we can't really expect that the lines will have some structure there. They can look as, they can take whichever form they want, they can be at whichever angle they like. The estimate will still be extremal. So we'll find structure in for joints that have fewer lines passing through them. And those are the joints with at most L to the 1/2 lines through each. This is sort of natural bound that comes from some Trotter that we'll see in a minute. In any case, we have that these joints can be split in two parts. So for every small parameter epsilon, which we won't really care about here, these joints can be split in a good part and a bad part. The good part satisfies an exceptionally good estimate. So it's so much better than the one at the top because the exponent on the left is much, much bigger than the exponent on the right. So it is almost 2, the exponent on the left. And the bad part, I don't know, it's my favorite part, so we called it bad, actually has structure. We call it nearly planar, this structure. It will mean that the joints and the lines forming them, the bulk of the lines forming the joints, cluster on planes. And these, I will explain what it is in a minute. And these are the joints responsible for however bad the top inequality is. Without them, you get better estimates. So this is interesting because in R3, for the maximal Kakeya conjecture, the best estimates that exist are due to Wolf, and he proved them under the condition that cubes don't cluster on planes. So knowing that cubes don't cluster on planes gives you something. We don't know how good the thing it can give us yet. But in any case, there is a similar spirit here that if lines cluster on planes, the incidences become too many and you get a bad estimate in some sense. Okay, so what is planar structure, first of all? It has nothing to do with joints, but I'll be saying joints because I'm used to it. So the picture looks a bit like what you would expect. Here's a picture. It means that the bulk of the lines responsible for the incidences belong to planes. They live on planes. So we have here certain blue joints that live on the blue plane, and the incidences essentially come from lines on that plane. Same for the red plane. And there is more than that, so we'll see exactly what it means. So I take away the colors of the lines to begin with. We say that the set of points has planar structure, at least with respect to the set of lines it lives in, if we can partition the points in different sets that live on different planes. So here, the blue joints live on the blue plane, the red joints live on the red plane. We make a choice for every joint, and we stick with it. There's such a partition that has a nice property. So first of all, I look at all the lines in the blue plane that contain blue joints, so that participate in incidences for the blue joints of that plane. So those blue lines are responsible essentially for all the incidences for the blue joints. So this is what it says. If I pick any blue joint, the number of lines through it in general, in the big family, is comparable to simply the number of lines through it on that plane. So this tells me that if I want to count the incidences from within one on a plane, for joints on a plane, I can pretend that they only come from lines from within that plane. And then I also know, that's the second thing, that lines that contribute in one plane don't contribute to any other plane that they live in. So the collections LP, so those blue lines, have nothing to do with the red lines. Those, this is a partition of the lines as well, the way we do it. Okay, so what does this really mean? It means that a line that could contribute to both will not. So a line that can contribute to incidences to both these planes that I drew is a line in their intersection, their intersection line. So I'll go and draw it. I see that it contains some blue joints, so it's blue, at least. And it can't be red. That's what property 2 says. So it cannot contain red joints. Okay, that is what it says. It can't contain red points at all. Which means that it has, say, it contains blue joints, it has a fan of lines through it, along the plane, through each joint, but it doesn't have fans coming out of it, living on the other plane. So it means this configuration is forbidden if we have planar structure. If a line contributes to joints on one plane, so the left one, it cannot also contribute to joints on the right. It will only contain red and not blue, or vice versa. Okay, so these things, morally, what do they say? They say that if we want to count incidences for joints, eventually if we show they have planar structure, we can just count incidences within every plane independently and then add up, and there is no double counting when it comes to joints or lines. So we can just isolate our attention in each plane individually. So practically, this is helpful. In a more, I guess, intuitive way, this is useful because it says the more lines cluster on planes, the worse it is for incidences. The more incidences you get, which is a common denominator in all these problems. All right, so let's see. Some ideas about the proof. Okay, we'll take a set of lines, a set of joints that they form. And to make our lives easier, we'll focus on joints with a specific number of lines through each. So JK will be the set of joints with about K lines through each. So between K and 2K. And our estimate looks a bit simpler this way. This is the kind of estimate we want. For every joint in JK, we have K lines through it, so that's what we have to raise to the 3/2. All right, we'll use two basic tools for this that have to do with Euclidean space, so both fail in finite fields. So one is the Samaredit-Trotter theorem. The Samaredit-Trotter theorem says that it's not just for joints, of course, it's for general points. You can control the number of points according to how many lines pass through each. So I should say that the second estimate is, gives us a very trivial case in terms of the desired inequality. So if we are in the second case, where we seek to have large K, so many lines through each joint, then we can use this bound all over K to the left-hand side of our goal inequality, and we see that the inequality becomes completely trivial. So we'll forget about that. The interesting situation is the first one, for few lines through each joint, and this is where our L to the 1/2 distinction between structure and no structure comes from. In the trivial case, you sort of have bushes of lines, and it's not so interesting right now. So the second tool will be polynomial partitioning. So this was developed by Guth and Katz in 2010 to solve the Erdős distinct distances problem in the plane. And it has really revolutionized incidence geometry since then. The idea is the following, and why it works. So we get an arbitrary set of points in R3, and we get a quantity that's bigger than 1, so that it can play the role of the degree of some polynomial. And this theorem says that you can chop up this set of points in sort of equal parts using the zero set of a polynomial of at most that degree that you chose. So we'll see how that is useful. So this is what it says. We can find a polynomial of low degree, as low as we chose, whose zero set splits the space in a specific number of parts that depend on the degree, and each part contains at most its fair share of points. And of course, we may have a lot of points on the zero set as well. So the way you do this is first, you look at the set you have, and you bisect it with a plane, say. So this is the first step. And when I say bisect, I mean that, okay, maybe many points are on the zero set, but at most half are on the left, at most half are on the right. Now we have two sets, one on the left and one on the right, and we can bisect both with the zero set of a low degree polynomial. Now we have four sets. We can bisect all of them simultaneously with a zero set of a low degree polynomial, and so on. And we stop whenever we want to stop. The degree we accumulate along the way is pretty small because every step uses small degree. So, okay, why is this useful? So in a from a practical perspective, it chops up the points in smaller parts. So it's like a divide and conquer approach. If you understand each part, maybe you understand the whole thing. And maybe it's easier to understand small parts because you can use induction, I don't know. But I think the deeper reason why it has really worked with point line incidences is that, as we said earlier, the incidences tend to be many when the lines cluster on low degree varieties, such as planes or W-rolled surfaces. So you get a lot of incidences then. It's something like an extremal configuration you have to deal with eventually. And this polynomial partitioning gives you a variety to work with that can contain a lot of your points. So it's as if it gets you to an extremal case without you having to show that it's extremal. Anyway, that's the idea. So the goal is to deal with all the level parts, but in the end focus on the zero set, on the points on the zero set. And that's what we'll do as well. So returning to the proof, remember we want to show a specific estimate with 3/2 exponent on both sides. So one case is the case for which this trivially holds because we actually get something way better. There are cases for which exceptionally good estimates hold in the sense that the left-hand side exponent is very big. We can forget about them. We call them good case. They are boring case. And they give the good joints, the exceptionally good joints from the start. The interesting case are the bad ones for which we can't expect exceptionally good estimates. So we focus on JK for each such bad K. And we show that their union has nearly planar structure. It's not quite planar, but each JK will have a large subset such that their union has planar structure. That is all. So that's what nearly planar means. So you can refine so that you get planar structure. Okay, and as we said, we focus on each JK independently. We know that we have about K lines for each such point. And what we'll do is we know that some Redet-Rotor holds for these joints. So we have some bound for these joints. And what we'll want to do is to partition with a polynomial of a specific degree. And that's where the degree will come from. We get a quantity here that's non-trivially bigger than 1. So it can play the role of the degree of an interesting polynomial. The reason we'll use this degree comes from many parts of the argument, but I'm telling you in advance that this is what we'll use. So we will partition with using the polynomial of such degree. And you see that for each different K, I use a different degree. So for a K prime, I have JK prime below and K prime to the 3. All right, so this is how we split. And if you want to see the exact statement, that's what it is, the partitioning statement. There is a polynomial of at most that degree, that splits in D to the 3 cells, and each cell contributes its fair, at most its fair amount of joints. Okay, and as usual with such situations, we have two cases. One is the cellular case, where the majority of the joints live inside the cells. And the other is the more interesting one for us, where the majority lives on the zero set. And the cellular case we deal with in a very standard way. So this is not really the new part of this paper. What you do is you focus on a cell of average behavior, and you just work there. And it's quite easy to deal with it. We actually show the cellular case cannot exist, given our choice of degree. Okay, I have slides here if you want for later, but for now, I just want to move to the algebraic case. Okay, so here we know that we have a lot of points that live on the zero set. What we want is to show that, so the zero set is red for me here. I want to show that the lines through each of these joints are also essentially red. So I want to show that most of the lines through each joint live on the zero set as well. So that I do have a lot of structure there. And not only that they live on planes inside the zero set. So that the zero set has certain planes in which the lines live. So that is useful for later. So using this, we'll show that these joints in JK have nearly planar structure. And the hard part is to unite all JKs together, all the bad JKs, and show that their union has nearly planar structure. So that is really the new part, but to get you there, we need to do this first. So this is sort of a more standard refining process to show that the lines live on the zero set. On the left picture, I have the joints, the average looking joints. And on the right, I look at the average looking line. What do I mean average line? I mean line that contributes the average number of joints at least. Okay, so these lines are essentially responsible for all the incidences, or for a good proportion of the incidences, and I can pretend that all of the lines are like that. So I have about k average lines through each joint. Now, so the average line contains many joints, but we know the joints are on the zero set. So the average line hits the zero set a lot. And if this happens more times than the degree, it will be completely engulfed itself by the zero set. And that's what we have. So we can show that the joints it contains, the times it hits the zero set, are more than a multiple 100 times the degree, I don't know. And if it wasn't the case, we'd remember what the degree is, and we'd get a contradiction, we'd get an exceptionally good estimate for these joints, which can't be true. Okay, so we know that the line is red, the average line is red, because it hits the zero set more than the degree times. So here it is, red, and on the left I have a lot of red lines, about k, through each average joint. So we have proved that there are many lines that live on the zero set through each joint. Now I want to show that they are in planes in the zero set. That's more than before. Okay, so to understand that, I need to understand each one of these average lines on the left. So I look at the average line. It contains some average joints. Each of them may be a critical point of the zero set, meaning that the gradient of the polynomial is 0. And there is a good chance that tangent spaces don't exist at such points. And the other points may be regular, in the sense that tangent spaces definitely exist at those points, and the gradient is non-zero. Okay. I have more information than that, and that's what I need here. Each of these points that the line contains is an average joint. So, like on the left, it must have a lot of other average lines through it. So I draw them. And this tells me something interesting for the regular joints. In particular, I look at all the lines in the zero set through them. I know that the tangent space exists there. So all the lines must cluster on that zero set, on that tangent space, on the tangent space to that zero set. So that is saying already that these lines should cluster on a plane. But what we'll use right now is that the existence of many lines in the zero set through this point means that the second fundamental form will vanish there. So the point, because it will have many such lines through it, will be flat, meaning the second fundamental form will vanish. Okay, so from the left picture, the many lines through each joint, either a lot of them contain a lot of critical points, so they will be infected by that, they will be fully critical, or a lot of them will contain a lot of flat points, and they will also be infected by that. So that is what we do. If we have more than the degree critical points along a line, we know that the line is fully critical, all of its points are critical. And the good thing about that is that such lines are very few. There are very few critical lines by Bezout's theorem inside the zero set. So yeah, there may be critical lines in this left-hand side picture, but we know there are very few. Now, another case is for the average line to contain many flat points. And this does infect almost the whole line. So it means that except for finitely many points along the line, everywhere else the second fundamental form will be zero. Can we control such lines? Let's think about this. Let's look at the zero set. It looks a bit like this. It has some planes potentially in it and some curved parts. Now, a plane contains infinitely many flat lines. The second fundamental form vanishes everywhere. So we can't control flat lines on the planes, but we can definitely control them outside the planes. So we have very few of those as well. Okay, so to sum up what we just said, I do a new picture. We have a lot of joints in the zero set. Through each, we have a lot of lines in the zero set. So everything is red. We can pretend everything is red in this picture. And each of these K lines is in one of three possible categories. It's either a critical line or flat living inside outside planes of the zero set, or flat inside the planes of the zero set. And the first two categories contribute very, very few lines. Okay, because these are very, very few, we can pretend this case doesn't exist. So how do we do that? Okay, I don't want to get into it. There is a multi-joints estimate that we can use. So multi-joints estimates are about, say, we have three families of lines forming joints. Can we control the number of joints according to the sizes of the three families simultaneously? So if from two sides we have very few lines contributing, then we know the joints will be very few. So these d squared at most lines are responsible for, they participate in creation of very few joints. The rest are the ones that form the bulk of the joints. And you see that they're flat lines and they live inside planes in the zero set, which is exactly what we wanted to do. From this picture I drew of the zero set, we can completely ignore the curved parts. We can only look at the planes in it. And we know that the joints and the lines, bulk of the lines forming them, cluster there. One detail, also these joints that we're talking about here are in principle flat points of the zero set. Why? Because if we had a lot of critical points, a lot of them would cluster on one of these flat lines and they would prevent it from being flat. They would make it critical. Okay, so anyway, we have a lot of flat joints living in a lot of flat lines in the planes of the zero set. The picture is this. It's very similar to what we wanted to achieve. It's better than what we wanted to achieve, actually. We can show that these flat joints have planar structure. Why? Actually, the intersection of these two planes cannot contribute any such flat joints. Why? Let's look at it. It is the intersection of two planes in the zero set. So this line is critical, fully critical. We can't have a tangent space anywhere along this line. Therefore, it can't contain any flat points at all of this variety. So it cannot participate in the forming of any joints at all. So these joints, the flat joints, clearly have planar structure for every given K. Right, so this line can't contribute to either plane. Okay, we have shown something, but that is not so interesting, because if we take the union of all such bad JK, we can't say anything about whether, we can't directly say that this union should have planar structure. Look at this picture. These are the flat joints in JK. They are arranged in planes in the red zero set we talked about. And let's look at another K prime. The same analysis holds there. We have a bunch of flat joints there that live in a blue zero set that comes from that analysis. So each has planar structure, but if one picture falls on top of the other, like this, then we see that there is a line here in the intersection of the two planes that has contributes to joints on the red one and contributes to joints on the blue one. And that's a big problem. So a union of things with planar structure doesn't have to have planar structure. So that is I guess the harder part of this argument. How do you pick out big subsets of these two sets such that their union has planar structure? Okay, so let me just finish by talking about the main idea on this. We want to show that this specific picture we'll draw now can't happen very often. So we look at the analysis for two different K. So we have a K on the left and the red plane inside that red zero set, and the blue plane on the right corresponding to another K prime for that blue zero set there, in that blue zero set. And these intersect along a line. I don't want this to happen a lot. So I'd like very few red joints to participate, to be in shared lines like this. So yeah, I want them to belong to lines that only contain them and nothing more, essentially. I want this picture to happen rarely. So what's the idea here? What information do we have so far? Okay, whatever is red lives in the red zero set. Whatever is blue lives in the blue zero set, but there is more. The red joints were flat for the red zero set. In particular, there were regular points. The tangent space exists there for the red zero set. And similarly, the blue joints were regular points for the blue zero set. We'll use that here. In particular, it implies that the red plane cannot be blue as well. So the red plane cannot live in the blue zero set. It lives in the red zero set. It can't live in the blue because if it did, if it was also blue, we'd have two planes, or blue planes in the blue zero set. The line along which they intersect is a corner. We can't have any tangent space there. All the points are critical along that line. So these blue joints that are regular points wouldn't be there. So the existence of regular points for the blue set, zero set along this line, ensures that the red plane cannot be blue as well, cannot be in the blue set. Okay, so that's what we want to use. That's one part of the things we use, but that's what we'll focus on. Okay, so this means that amongst the red lines here, very few can be blue. If you got a lot of blue lines on the red set, it would infect the whole blue plane, the whole red plane. It would infect the red plane, it would become blue. So let's explain this. Let's look at the lines, the red lines in this picture. If this picture repeats itself a lot, which we don't want to be true, then a lot of red joints will cluster on such lines, and one of them will contain many. So we can pretend we have a lot of red joints along this line. And since K red lines pass through each, we have a lot of red lines in this picture. Okay. Now some of them may also be in the blue zero set, may also be blue. Say more than half, or more than half are just red, so they are only in the red zero set and not in the blue one. Okay, the interesting case is the left one. That's what we'll explain here. So I pretend that more than half of the red lines are also blue, so they're actually purple. Anyway, I draw them blue in this picture. And now remember, the red plane is not blue as well. It's not in the blue zero set. So these blue lines it contains can only be at most a degree of the blue zeros. If the pk prime polynomial was vanishing on more than its degree lines along the plane, then it would vanish on the whole plane. Okay, so that is the result of this. All the lines we know we have, the red lines, are at most the degree of the pk prime polynomial, the blue zero set. Okay, so we get some bound for jk that unfortunately depends on k prime. And actually the second case that I won't deal with yields the exact same bound. So from both cases we'll get the same bound. Okay, I remember what degree I used for the k prime case. It's the same as I used for k, but with k prime instead. It comes from some Reddit-Rotor, just the same way. Okay, and yeah, I get a bound on jk, but it doesn't tell me much because I know nothing about jk prime and k prime. If I knew that I can replace this denominator by the one for jk, so if I knew that this inequality holds, in other words, that the k denominator is smaller than the k prime one, then I would have a very nice, interesting bound anyway. I would rearrange and I would get that jk satisfies an exceptionally good estimate, which can't be true. I assumed k is bad. So assuming that this line contains a lot of red joins, or in other words, that a lot of red joins participate in bad configurations like this, I got a contradiction. And you'll say, this is a big if. How can I know that such a thing will happen? It's not such a big if, because one of the two quantities will be smaller than the other, for sure. So if it doesn't happen for jk, it will happen for jk prime. And I can do the exact same process for jk prime. So what we do is we create an algorithm where every time we work with a k, and the k primes we're looking at all satisfy this nice inequality. And doing this carefully, you can get, you get that this doesn't happen very often. And I guess this is it. So yeah, all this process of working with point line incidences has really helped with restriction theory too. So since 2014, people have been using these polynomial partitioning ideas to understand waves. And it seems that the interesting interaction of waves happens close to varieties, just like for point line incidences. So yeah, this is what I want to say. Thank you very much.